Hello, everybody. This is material from chapter 3 in our book. You can follow along with the PowerPoint slides that are posted on Canvas. Okay. So chapter 3 is about some more scientists and the development of astronomy, as well as the the laws of physics. So the universal laws of physics, we're going to need to learn about those. Okay, so we're going to actually skip over a lot of time, actually about 1,500 years, really. But you'll remember from chapter 2, we finished with a geocentric theory from a Greek philosopher, astronomer by the name of Ptolemy, P-T-O-L-E-M-Y. And the Ptolemaic version of the universe was that the Earth was at the center and then everything else went around it. So that and the thinking that went along with that, Aristotle's was a very important, influential philosopher. His ideas actually ruled the thinking for about 1,500 years. In Europe, actually things were kind of tough. Western Europe, actually with the fall of the Roman Empire, began to have more problems. There was a plague and everything. But in the Middle East, it turns out astronomy was being developed, and science in general was being developed and sustained. And then it was taken back to Europe by the invaders in the 1400s, 1500s. So we're going to actually jump forward in time to, and we're skipping over a lot of stuff. I really would love to know more about it, but I don't know that much. But we're going to skip forward to a man by the name of Nicholas Copernicus, who published a book known as The Revolutions. And in this book, he postulated that the Earth is not the center, that the sun is the center of the universe, and the planets go around the sun. This is a sun-centered theory, or a heliocentric theory. There are a couple of things that you want to know about this theory. Copernicus said that the sun was at the center, that the planets orbit on perfect circles around the sun, with the closest planet being the fastest in its orbit around the sun, taking the least amount of time. And the further away that you go from the sun, the slower that you travel. Okay, so this is a pretty beautiful theory, and actually, in fact, it was adopted by scientists pretty quickly, and it gave us a very, very simple explanation for retrograde motion. So it turns out retrograde motion can be simply explained using this heliocentric theory as an inner planet passing an outer planet. So whenever that happens, it looks as though the outer planet is going backwards. Now, the outer planet never stops moving forwards, right? It's always moving forwards. But if you're moving faster, for example, on the freeway, and I did post a little video clip showing exactly what this looks like when you pass a slower vehicle in the right-hand lane, right? For example, it looks like they're going backwards. They're not going backwards. They're just going a little slower than you, but relative to you, they are moving backwards. So you see that. So we're riding along on the Earth. We see Mars going backwards, and you can follow the progression. Mars is going forward, prograde motion, and then retrograde motion, and then back to prograde motion. And so this takes a while, right? It takes about 6 months for this process to occur. And so actually something important, every planet that we look at, we will see doing retrograde motion. Now you say, well, not all the planets are further away from us, from the sun compared to the Earth. Some of them are closer, right? 2 of them are closer. Mercury and Venus are closer. But it turns out it doesn't really matter if you're closer or further. At some point, you're going to see the other planet going in the reverse direction from its normal motion, right? What we call retrograde motion. So if we were on Mars looking back at the Earth, we would also see the Earth change directions. And that's the idea. It doesn't matter if you're closer or further. It's basically the difference in the speed that leads to retrograde motion. Very, very simple. Now, unfortunately, when the Copernican model was used to predict the timing, it was really bad. In fact, it was much worse than the Ptolemaic model was. And if you think for a second, why do you think it would be so bad, right? What was the major reason? It turns out the major reason is that Copernicus thought that the orbits were circles, perfect circles. He was wrong about that, unfortunately. And that turns out to be enough to cause problems. But it is a simpler theory, and therefore it did win out. And we actually use this theory today, right? You should know that. So one of the predictions of the heliocentric theory is that planets that are closer to the sun than we are, and that would be Venus and Mercury, are going to have phases just like the phases of the moon. And they are the only ones that can have phases like the moon. And the reason is that if you're further from the sun, you look away from the sun than we are, like Mars or Jupiter, Saturn, any of the other planets, Uranus and Neptune, then when you look away from the sun, you're really kind of looking at a planet. It will always be either gibbous, nearly full, or full, right? That's it. And the reason is we're looking away from the sun. But Venus and Mercury can be near the sun. They're always near the sun, as a matter of fact. So a couple of things I can just show you real quickly. Let's go ahead and let's try to jump over to our Stellarium program. And let's take a look at Mercury and Venus. Okay, so I'm going to actually go ahead and do a search here. And I'm going to type in Mercury. Let's do Mercury. And as you can see, Mercury and Venus actually are right next to, they're always near the sun. So one of the things that you should be aware of is that Mercury and Venus have this kind of interesting names, right? That they're actually misunderstood, right? People thought they were stars. They're not stars. I'm going to go ahead and pause, and then I'm going to do something. I'm going to move time forward. I want to show you that tonight, in fact, would be a great night for you to observe Mercury and Venus. I saw them last night. That was really cool. Let me change the background so that we don't see so much. I'll just put the ocean. I like the ocean, actually. That's kind of cool. So if you look for the setting sun, you'll notice that the sun is going to set, right? The sun is going to set and Mercury and Venus will be up tonight. This would be great. Try to look for this tonight. It would be really neat for you to see it. Mercury is normally really difficult to see because it's so dim, but actually tonight, maybe tomorrow night, well, actually Mercury's going to be bright for a little while. You'll be able to see Mercury. It happens to be easier tonight though, because Venus and Mercury are very close together. So if you find Venus, which will be easy, you'll find Mercury just a little bit higher and to the left, okay? So these actually right now, Mercury and Venus are both evening stars right now. That's what they're known as, but they won't last as evening stars for very long. And so actually, if I go ahead and press the space bar, Mercury will go into the middle, and then I can zoom in and I can see that it is actually a gibbous, right? It looks like a gibbous. Now, if you watch, I'm going to go ahead and hide the land and hide the atmosphere. And then I'm going to watch it progress. Watch Mercury's phase, right? And you can see that now it's becoming a crescent. And in fact, now it's a new Mercury, right? And now it's a crescent again. But you'll notice that it's lit on the other side. Why is that? And the answer is because it's over here on this side of, where's my sun? Where's the sun? There's the sun. The sun is over there now. So if you look right here, actually, it turns out I'll turn the ground back on. You can't see the sun yet. Hold on, let's go back. That's what I wanted to see. So there's the sun, but Mercury has set because it's actually in front of the sun. So this time what I want to do is go back to sunrise. Let's go back to sunrise. Go back to sunrise. We're going to make the sunrise. Yeah, I'll turn the atmosphere back on so you can really see it. Okay, it's actually going to be hard to see, but you'll notice that Mercury and Venus are up before the sun. So what does this mean? They're actually called morning stars in this case, okay? So they are morning stars. So Venus and Mercury switch between being morning stars or evening stars, depending on where they are in their orbit around the sun. And so that's kind of an interesting little fact. And they are the only planets that can be seen as crescents, okay? So if I look at Venus right now, it's a crescent as well, okay? So let's go back to Mercury, and I want to show you Mercury go through its full cycle. Okay, there's Mercury, and I'm going to press space to center it, and I'm going to turn off the atmosphere and zoom in. And there we go, it's a little crescent. Let's go ahead and advance it. And you can see it's getting more full. So like a first quarter, right? It's a gibbous, and now it's just about full, right? And then it's getting less full, right? Doesn't take as long. It actually only takes about 4 months for one full cycle. And you notice it's getting bigger because it's getting closer, and then it's gone. Goodbye, it's new. All right, so switching back, let's go back to our PowerPoint. Okay. So only Venus and Mercury have crescent phases, right? All the other planets that we look at are further further away from the sun than we are, and we will see them as gibbous or full. Okay. All right. So let's talk about this fellow. This is actually going to be our next character. You need to know the name Tycho Brahe, if you want to be an American and say it like that. He was a nobleman, and you'll notice he has a golden nose. And this is a story, and I don't want to not tell you. So actually, let me just tell you a story. It turns out Tycho was a hothead, and when he was young, he was a mathematics student at his university. And apparently, when he was about 21, he got into an argument with someone, and they claimed that their university was better. He thought his was better, and they had a duel. And at that time, you didn't have guns, you had swords. And in this duel, he lost, and his nose was lopped off. And so he is actually a nobleman, came from a rich family. He was able to purchase, some pretty fancy noses, and he wore this for the rest of his life. It's kind of an interesting story. Another interesting story will be how he died, but I think I'll leave that one for a little bit. So we actually give him credit for being one of the most careful naked eye astronomers. This is a time before Galileo, before the telescope, but he actually built an enormous astrolabe, which is a device for measuring the locations of the stars and planets, and he tracked them. And so this is actually a picture of his apparatus. It was a 2 or 3 story tall apparatus that gave him the ability to measure the angle to the planets more precisely than anybody had ever done before. And so we give him that credit, right? He is the greatest natural naked eye astronomer. So he collected data for more than 25 years. You should know also, he was a geocentrist. He believed that the Earth was at the center of the universe. And I think I might have mentioned it, but let me mention it again, that the reason why Aristotle thought that the Earth was not moving, and the reason why Tycho thought the Earth was not moving, is because they could not observe stellar parallax. And parallax is the idea that, actually, I'll just look at you guys for a second. Parallax is the idea if you hold your thumb out at arm's length, right? Hold your thumb out, and you wink with one eye, then the other, your thumb changes position, right? That's called parallax. When you observe from different positions, you see something move. The further away it is, the less it moves, right? And the closer it is, if you bring it really close, the more it moves, okay? So they couldn't observe stellar parallax. They believed that the Earth was not moving. Unfortunately, the reason they couldn't see it is because it's just too small, okay? So Tycho, though, recorded a lot of data, and then something happened, right? When he was not too old, in his early 40s, actually, he attended a party, a feast, actually, of some kind, And then something happened. Back in those days, it turns out that you were not allowed to leave the table unless the lord of the manor gave you permission. And so imagine you're sitting there feasting and drinking your mead, your big old goblets of mead, and then you have to go to the bathroom. Well, it turns out in this party Tycho was at, the Lord had passed out drunk. And so he sat there, you know, because he's a very polite fellow, he didn't leave the table. And something bad happened. It turns out his bladder burst, and that's not a very good way to go. And so for the next 3 days, he was in incredible pain, delirious with fever, and he actually died, right? So he died from this, we think, from this infection, from his burst bladder. But before he died, he actually asked the Lord to adopt his, to take his assistant to be the royal astronomer. Sorry, I never told you, he was the royal astronomer for Denmark. But anyways, to take his assistant to be the royal astronomer. And they did. And the name of the assistant, you need to know, is Johannes Kepler. So Johannes Kepler, again, was a mathematician and a scientist, and he was the one who finally got all of Tycho's data and managed to interpret it. And so this is a pretty cool thing, right? So we want to know, what did Kepler do that was so special? Well, he basically figured out the meaning of all of the observations that Tycho had done. Okay, so we're going to learn that Johannes Kepler made what we call the laws of planetary motion. Okay, so you need to know them in order and what they are, and then more importantly, what they mean. Okay, so law number one, the orbits of the planets are not circles, they are ellipses. Okay, so there's some terminology. You can see an ellipse is a little stretched out. And the idea is when you had a circle, there's a single center. But with an ellipse, that center gets split. And there are two centers. They're called foci, right? So there's two foci. So the first law states that the orbits of the planets around the sun are ellipses, and the sun is at one of the foci, but nothing is at the other foci. Okay, so this is an important idea. I'm going to go ahead and switch to your. I'm going to actually draw a little something for you that you need to know. There's a word called eccentricity. Eccentricity is how stretched out something is, how elliptical it is. So something that's very circular, like a perfect circle, is not eccentric. It has an eccentricity of 0, right? But something that's more stretched out is going to have an eccentricity which is not 0, right? So instead of a single point at the center, right, in single center, we have these two foci. So the more these are separated from each other, the greater the eccentricity will be. So this might be 0.2, for example. So eccentricity is a number between 0 and 1, right? And the bigger it is, the more stretched out it is, the more elongated it is, right? 0 is a perfect circle, and 1, it actually can't be 1 because it won't be an ellipse anymore. Okay, so this is called an ellipse, stretched out circle. So the other thing that you need to know is the long end, the long side of the ellipse is called the major axis. Actually, the long length, I guess, is called the major axis. And that means half of it, right? Half of it is called the semi-major axis, okay? And this one is called the minor axis, okay? This is the minor axis. So you got the major axis, the long edge, and the shorter edge is the minor axis. Semi-major is half. And we use the letter A to describe the semi-major axis. Okay, you need to know that, okay? All right, so the planets orbit on ellipses with the sun at one of the foci. Okay, number 2, this is the second one. this law of equal area. So this is the law of equal area. It says that if you connect a line with the planet and the sun, that line will sweep out an area, and the area will be equal area in equal time, right? So if this is 1 month here, then this is 1 month here. So this is the law of equal area. What does it mean, right? So this is the part that you need to understand. What is the meaning of the second law? And so the meaning of the second law is really quite beautiful. I actually like to call it the law of elliptical pizza. No, sorry, the law of equal area. And the idea is, I make a joke, right? That imagine that I start a company that makes elliptical pizzas, right? Elliptical pizza. And so what you're going to do is you have your foci, right? And you're going to have a slice of pizza right here, right? This is one slice of pizza. But the idea is everybody gets the same area or the same cheese, right? Same amount of toppings, whatever the toppings might be. So we're going to talk about, this is our sun right here, right? The sun's in the middle, the planet is over here, right? And we're talking about it's moving from one side to the other. If you remember that we had names for when the planet is closest to the sun, this is called perihelion, perihelion. And we have a name for when the planet is furthest from the sun, that's called aphelion. So if I want to have equal area, right, that's this part here. How do I get equal area? Well, this is kind of a squat, a shorter slice, right? It's going to be wider. The way that I'm going to have equal area is going to be a long, skinny slice, right? These have the same area, about the same area. So equal area and equal time. So what's different, right? Well, what's different is, do they have the same crust? No, they do not have the same crust. Okay, so people who like crust, which slice do you want, right? Well, you want this slice, right? And people who don't like the crust, well, here, we'll give you this slice over here. It's kind of something for everybody. So what is the meaning of the equal area? This is important, right? It means that if you're closest to the sun at perihelion, you get more crust. Well, what that means is the planet travels further. The planet moves faster. Actually fastest, right? It moves faster here and slower here. Faster at perihelion and slower at aphelion, right? The planet travels slow, moves slower. Actually, the fastest is right here and the slowest is right here. Okay, so that's the meaning of the equal area. Okay. All right, so that's law number 2. All right, here we go. And now for the third one. The third one is the one that some people don't like very much, and I understand it's okay. But you're going to need to learn how to do it. So here we go. Law number 3, the law of periods. Okay, so this is kind of this is the mathematical law. If you look right here, I'm going to change it just slightly because they messed up just a little bit. It says that the period, the time it takes to go once around the sun, is called the period, is E squared equals the semi-major axis cubed. Okay, so actually let me go ahead and write that down for you the right way. This is what it says, right? The period squared equals the semi-major axis cubed, right? And this is an important thing. You need to measure, so this is actually, I'm going to put a bracket around the P. When I put something like this, it means the units of the period. That's what it means. And the units of the period are years, right? Years. And the units of A, which is the semi-major axis, are astronomical units, AU. Okay, so let's go ahead and start off with the planet Earth, which you guys know. What is the distance, the distance for the Earth? Well, semi-major axis, right? Turns out for the Earth, it's 1 AU. Also the average distance, by the way, you don't need to know that, but that's what A also represents, the average distance. So the average distance of the Earth to the Sun is 1 AU. What is the period for the Earth to go around the Sun? Well, it's 1 year, right? So let's just check this formula. P squared equals A cubed. Does it work? Does 1 year squared equal 1 AU cubed? And you can see 1 squared is 1 times 1, and 1 times 1 times 1. Yeah, it works. Perfect. Great. But actually, we're not using it for the Earth. We already know the Earth, right? What we want to do is use it for another planet. So what if I tell you, this is kind of a neat thing. What if I tell you that, let's see, what if I tell you? What if I tell you that Jupiter is 5 AU from the Sun, okay? So what I would ask you to do on a test is, if I give you the A, I would ask you to try to figure out what P is, okay? So I'm going to show you how to do this. It's not going to be that hard, and I'm not going to give you a really tough problem, right? It's going to be pretty simple kind of problem, but let's try it out, okay? Let's go ahead. Let's see. So P squared equals A cubed. I don't know the P, so I can't put anything in, but I know the A, so I can put it in. So P squared equals 5 cubed. That means 5 times 5 times 5, which is, I'm pretty good at mental math, 125. Now, again, we're not worried about the exact answer, just close enough, because this is a multiple choice question. So here's the question that I might ask you. What number times itself is close to 125? So 10 squared is 100. 11 squared is 121. 12 squared is 144. Well, so that's pretty big, right? So what's the answer? It's pretty close to 11 years, right? And that is actually really close to the right answer. It takes Jupiter actually almost 12 years, it turns out, because it's not 5, it's 5.2. But anyways, it's close enough, right? It is pretty close to 11 years. You would go ahead and answer that. Let's try another example, just because I want you to be feeling confident, except this time I'm going to go a little bit, no, I'm not. I'm going to keep going the way I'm doing. Never mind. I'm going to tell you Saturn is about a distance of 10 AU on average from the Sun. And so now we're going to write this down, P squared. So we're trying to find P again, right? P squared equals 10 AU cubed, right? That's 10 times 10 times 10. That's 1,000. Okay. Now I'm not gonna worry about the exact answer, but I want to try to figure out what number times itself gives me 1,000. So if I started with let's say 20 squared. What's 20 squared? 20 squared is 400. How about 30 squared? 30 squared is 900. What about 40 squared? 40 squared is 1,600. So it's pretty close to 30. And so you probably wouldn't be too surprised if I tell you that 32 squared is pretty close to the right answer, okay? But there is actually a way to do this with your calculator. It's a little, I don't know that I'm gonna ask you to do this, but if you wanted to do this, this is something you could do, right? And the way you do it is you go to your calculator, you type in the number you have, and you say what number times itself gives you 1,000, and the answer is you take the square root. So on this calculator here, I hit second function, and here it is, square root. So 31.6 is pretty close to 32, okay? So again, that's more than you would normally need to do. I wouldn't worry too much about that. Okay, so I'm gonna do one last example just because this is a little tricky. I'm gonna ask you to try to figure this out. I'm gonna tell you that the period of some object is exactly 8 years. Okay, I'm doing this on purpose because this is an easy one. It happens to be perfect, okay? And so the question, if I tell you the period, what is the average distance from the sun? So this time we're going to go p squared equals a cubed, but we have to figure out a this time. So here we go, 8 times 8, 8 squared equals a to the 3rd power. So what's 8 times 8? 8 times 8 is 64. So what number times itself again is 64? So let me try a couple. Let's try 2. 2 times 2 times 2. Well, that's 8. Never mind. Okay, that didn't work. 3. 3 times 3 times 3. 3 times 3 is 9. Times 3 is 27. All right, that didn't work. Too small. 4. 4 times 4 is 16. Times 4 is 64. Now, suppose I started with 5, by the way. Let's try that one. 5 times 5 is 25. Times 5 is 125. So you can see what's the right answer. The answer is 4 AU, worked out to be exactly the right number. Okay, so that's the tough one. And what it does, what it says is something important. It says that the further away you go, this is the idea, the further out you go, p squared equals a cubed. The bigger a is, the bigger p will be, right? The further away you go from the sun, the longer it will take you to go once around the sun, okay? And so we see that on this graph, right? If you look at the Mercury only takes 88 days, less than a year. Venus, 225 days. Earth, 365. Mars, 687 days, right? The further away you get from the sun, the longer it takes you to make one orbit around the sun. And it makes this beautiful formula that that Johannes Kepler figured out, okay? So that's our hardest one. That's the one you need to practice the most on, maybe, okay? All right, so this is another example. We'll skip that. Okay, here we go. And we are finally getting to one of our key players, the one who started modern astronomy, actually maybe not modern, but restarted astronomy using telescope, is Galileo Galilei. Okay, so he is gonna be a big fellow. Actually, I got to visit all of the universities where he taught in Italy. It's pretty neat, and I stood on the podium and felt his spirit fill me. I was so inspired. But anyway, Galileo Galilei, born in Italy to a rich family, and that will be important later on. We'll tell you why. He was a very curious fellow and actually discovered lots and lots of interesting things. And when he was pretty young, he made his first telescope. But he did not invent the telescope. The telescope was invented by a Dutch fellow, Hans Lippershey. And the invention was really made to spy on people or to use it at sea, right? It was a military device for spying on your enemy, or maybe a device for ship captain to look for land. And Galileo was the first person to look up at the sky, to look up at the stars. And in fact, the slides don't tell you everything. I'm going to tell you a few more things. But Galileo was a firm believer in the Copernican heliocentric model, and in fact was the first person to find evidence to support it. And so that's why we really want to give him recognition. So one of the things that he looked at, of course, is the moon. And in the Greek philosophy, everything in the heavens is perfect, right? The heavens are perfect. Any celestial object is perfect. But when Galileo looked, he saw mountains and craters. It was not perfect. And so Galileo saw the flaws, the imperfections, and this directly contradicted the idea that Aristotle had postulated that the heavens are perfect. So you know right there, we've got proof that things are not perfect, and they're more like the Earth. In fact, people believe that there must have been people, there were beings on the moon living their lives. We just couldn't see them, they were too small. He also was the first person to see that Venus had phases. He saw the crescent Venus, and he watched very carefully as Venus went through its cycle, and he was able to see all of the phases of Venus, directly supporting the Copernican model. Okay, so now we knew that Venus went around the sun, right? So that's a big deal, right? If you see Venus having all of the phases, then it must be going around the sun, not around the Earth. Okay. He also observed the 4 largest moons of Jupiter, and you need to know their names, so please write them down. There is Io, Europa, Ganymede, and Callisto. This is in order: closest to Jupiter, next closest, third closest, furthest from Jupiter. Io, Europa, Ganymede, and Callisto. And what he saw when he watched Jupiter was he observed these 4 moons. He thought they were stars, right? But they were actually orbiting Jupiter. He saw them changing position. As you can see in this, he had diagrams showing their position. And in one night, he would see them move. It got to be so that he could tell the time by their position. They were so regular. He imagined it was like a giant clock, actually. This is actually one of his biggest things. He also saw a couple of other things that are not mentioned in the slides. He saw spots on the sun. He was the first person to observe sunspots. And actually, I guess I can tell you a little bit about that. Let me go ahead and just talk to you. A couple of things to notice, right? So he saw sunspots on the sun. Now, he didn't look at the sun. Please don't ever look at the sun. If you use the special glasses that I gave you, you can look at the sun. Unfortunately, there's no sunspots probably. I didn't check today, but I'm pretty sure because we're in a quiet period right now. But he used a piece of glass that he held above a candle flame. And he held above the candle flame. And if you've ever done that, you know what happens is it gets black from the soot, right? The soot that collects from the unburned wax. And so that layer made it darker and darker and darker until he finally felt that it was safe. And he looked through that with just one eye, with his right eye. He looked at the sun. But he did that for many years until in his 60s, I believe about his 60s, he looked every single day, by the way, at the sun and counted sunspots and began a whole process that we continue to this day, by the way. Every day the sun is looked at and they count the spots on the sun. But anyways, Galileo did that until he was 60, and then he couldn't see anymore. He went blind in his right eye. So what did he do at that point? He shifted to his left eye and began to use that. And by the end of his life, he was actually pretty much blind in both eyes from observing the sun. So he saw the sunspots on the sun, the moons of Galileo, the Galilean moons, which went around, the moons of Jupiter, which went around in a regular way. He saw the phases of Venus, the flaws on the moon, and one more thing, right? He looked at the Milky Way with his telescope. And up until that time, people just thought it was a smeared out light across the sky. And Galileo was the first person to see that it was made of individual stars. So I don't know if you could imagine that wonder, but realizing that up until this moment, right, it looks just like a smeared out light. And he is the first person to see that it's actually made from individual motes of light, right? Individual stars. Pretty exciting thing. Okay, so Galileo was a big player. We will tell you he got into trouble, and actually he wrote a play called The Dialogue of Two Chief Worlds, where he made fun of the geocentric theory and supported the Copernican heliocentric theory. And the reason he got into trouble is not that exactly, but because the character that supported the geocentric theory was modeled on the Pope, and his name was Simplico, which means simpleton. So he basically offended the Pope and called him an idiot, a simpleton. And so he actually normal people would have been tried and killed, but Galileo's family was very rich and influential, and they were actually friends with the Pope. And so instead of being killed, he was placed under house arrest for the rest of his life. Now, in the 1990s, they finally said sorry. The Catholic Church actually said sorry to Galileo, we messed up. But anyways, yeah. So his house, by the way, was pretty nice. He had a pretty nice place to live, but yeah, he was basically in prison. Okay, so jumping forward in time, let's talk a little bit about one other thing Galileo discovered, is that all objects fall at the same rate of acceleration if you can ignore air resistance. Okay, so hopefully you watched the video, the Brian Cox video, but if I ask you the question, which one falls faster, a feather or a bowling ball, you know the right answer is a bowling ball, right? Feathers float slowly down to the ground, but that's because there's air in the way, right? If you take away the air, then in that video you saw the bowling ball and the feathers fall at the same rate, which is mind-boggling. You've never seen it, right? It's so bizarre. But this was one of the things that Galileo realized, and it was a pretty amazing feat to understand that. So he showed that Aristotle was wrong about that too, right? Aristotle was wrong about the perfection of the heavens, and he was wrong that the more massive objects fall faster. So anyways, you could think about that too. There's another, related idea. If you take two rocks and you hold them separately, they fall at the same rate. Well, what if you tie them together? You've now created a more massive object. But if you drop them, they'll fall exactly the same way they did when they were separate, okay? So anyways, all right, jumping forward, we need to talk about a few concepts that you need to know the names of. We've got the word force right here. A force is a push or a pull between two objects, okay? And if you have a force, something will happen, right? Force makes things happen. Second concept is mass. And mass is essentially the number of atoms that you have. We usually talk about it as weight, but weight is not the same thing as mass, right? Weight is the force of gravity that we feel. And it is true, the more mass you have, the more weight you have. But mass doesn't change when you leave the Earth, for example. If you go to space, you'll feel less gravity because you're further away from the Earth. Well, we're about to learn that actually. But you don't lose mass, right? Your mass will be the same whether you're on Earth or on the moon. On the moon, the force of gravity is 1/6 as strong. You weigh 1/6 as much, but you have the same amount of mass, right? Mass is just how much stuff you have. Okay, so you have some words here. Velocity is the, I don't like the definition. The velocity is the speed and the direction. Here, this is a better one. It's the speed and the direction that you're going. It is called a vector. Speed is just how fast you're going. Okay, your speedometer on your car measures your speed, but velocity would include which way you were moving as well. Acceleration is the rate at which you are changing your velocity. And so it's important to understand acceleration in the common language means to speed up, but in science, in astronomy and physics, it means to speed up or to slow down or to change direction or to do both, right? So acceleration is the rate at which you change your velocity. Okay, so I'm going to go ahead and tell you a couple key ideas with this, right? So concept of speed, right? Speed, right, is like 50 meters per second, right? I'm going 50, but actually 50 meters per second is the speed. When I put an arrow right here, then it becomes a velocity. So really, in case you didn't get it, velocity is speed plus direction. And it turns out you can draw an arrow to represent that. Now, what if I were to draw an arrow twice as long? What do you think that might represent? Instead of 50 meters per second, what do you think? How about 100 meters per second, right? Twice as long. So actually, this is called a vector. A vector is just another word for an arrow in science, but it's an important idea, right? It has two things. It has a magnitude, which is just the length, okay? And it has a direction, but it's pointed. Okay, so magnitude plus direction. So there are some really simple ideas, but basically, if you know what a vector is, I can tell you more about this stuff. So please understand. So a vector is an arrow. It has a magnitude or a length and a direction, right? So I could change the magnitude, I could change the direction, or I could just change the magnitude, right? Keeping the same direction, right? There's different things I can do. And these would represent different vectors or different velocities, perhaps, okay? So how do you change velocity? Well, it turns out the guy who's going to tell us all about that with his laws of motion is a man by the name of Isaac Newton, okay, who Principia Mathematica, he came up with the 3 laws of motion. You need to know them in order. And I'm going to write down for you my version of them. The book has a slightly different version, but the same ideas, it's just slightly different. Okay. And the 3 laws of motion, and then a 4th law, which is going to be the law of gravity. Okay. So here we go. The first law, it's called the law of inertia. Okay. And so the law of inertia says an object at rest will remain at rest, but an object that is moving will continue moving with a constant speed and direction. Another way to say that is a constant velocity. Okay, so I actually posted a little video clip for you showing you something that's moving. And moving with a constant velocity means that you're moving with a constant speed and in a constant direction. So the concept of inertia, so let's write that down for you, the law of inertia. So the law, number 1, so the laws of motion. These are Newton's laws of motion. Oops, I can't see. Laws of motion, according to Newton. The law of inertia is number 1. So what is inertia? What is inertia? In Newton's time, he didn't know for sure, but the idea it's how difficult, inertia is how difficult is it to change the motion. Okay, so inertia was how difficult it is to change the motion. We now know what inertia is. Inertia is mass. Okay, so something that has more mass is more difficult to move, right, or change its motion. So if I try to push on, let's say a little kid on a skateboard, right, like my son riding a skateboard. He likes to ride skateboards, by the way. I can't draw very well. What are you doing, man? I don't know. I'm riding on a skateboard, Dad. Okay, so if I push on my son, it turns out it's not that hard. I can get him to move really easily. On the other hand, back when I was a kid, my car would run out of gas. And my car, which is a big, giant, heavy car, right? It's a 63 Pontiac Le Mans. Okay, that was my car. And I would be there, and my friends and I would be driving around, and we run out of gas. And this was a massive car. It was a tank. And the reason I got to drive it is my dad gave it to me. But when you try to push on this, it is really difficult to move. So this one has a lot of inertia. This one does not, right? Okay, so it turns out it's really hard to move it. So okay, so first law, a law of inertia states that an object at rest wants to remain at rest, but an object that's moving will continue moving with a constant speed and direction, which just means constant velocity, unless acted upon by an outside force. Okay, so that is the first law. The second law is the formula law. Okay, the second law is the formula. It says F equals ma. It's a formula. It says that if you act with a force on something, then you will make the mass change its motion. And the word for that is accelerate. So the way that I read this is a force causes a mass to accelerate. More force causes more acceleration. Okay, so a couple of quick ideas here that you need to be aware of, right? A force causes a mass to accelerate. Well, what if you have a, what if you have, for the same force, what if you have a big mass? What happens? Well, you end up with a tiny acceleration. But that same size force, what if it's acting on a little tiny mass? Then what happens is the acceleration will be bigger for that small mass for the same amount of force, right? So if you look at this formula, the way it works is that the acceleration is equal to the force divided by the mass. Okay, so I'm going to talk about this real quickly because this is an important concept, right? The acceleration is, I've just divided both sides by m, right? The force is on the top and the mass is in the bottom, in the denominator, right? Numerator, denominator. So what happens is the force is directly proportional. I'm writing these words down so you know them and I could use them in the future. Directly proportional. And in the bottom, the mass is inversely proportional. I can't read that. Proportional. Okay. So what does it mean? When you are directly proportional, the more you put in, the bigger this part is, the bigger your answer will be. But better than that, if you double the force, you double the acceleration. Inversely proportional means the bigger this is, the smaller this becomes. So if you double the mass, what happens? You end up with half of the acceleration. It's called inversely proportional. Okay. So anyways, that's the way it works. Now there's a little bit more. It turns out that the force is going to make things happen the way that you push, right? So suppose that I have an object with a mass and it has a velocity that goes like this. What happens when you push like this? What's going to happen? You push in the same direction you're already going to go, or you're already going. And the answer is, you know what's going to happen? It's going to speed up. Going to speed up. Okay. How about this one? You're going forward, but this time you push backwards or you pull backwards, right? The force is the opposite direction that you're moving. What's going to happen? Some of you might be able to say it. You slow down, right? So if the force is with you, Luke, no, just kidding. The force is with you, you speed up. If the force is against you, you slow down, okay? That's pretty much it, right? Well, there's actually one more situation you have to be aware of. I'm moving forward. I got my velocity, right? But this time the force is not with me or not against me. It's exactly to the side. So what does it do? Speed me up or slow me down? And the answer is neither one. It can't speed me up. And so what does it do? It turns me, right? Turns me, or what turns, whatever, turns me. Okay. So the force is going to turn me. Okay. I guess it's me. Hey, there you go. Okay. So a force with you speeds you up. A force against you slows you down. A force to the side makes you turn. Okay. So these are the concepts of force. So force causes a mass to accelerate or change its velocity. So you can speed up, you can slow down, or you can change your direction. Any of those are called accelerations. Okay, so it doesn't just mean to speed up. Third one, the law of action-reaction. Okay, here are the words. For every force, there is an equal but opposite reaction force. Okay. And so the third law says that when you push on something, it pushes back on you, okay? So an example of that, so the law of action-reaction, this is the third law. Law of action-reaction. And what that means is, let's say that you, if you push on something, right? You push on actually, you know what? You can lean on the wall, for example. You can push on the wall. Whatever you do, if I push on the wall, and by the way, you don't need to know this, but the way that you measure forces, the units of force are called the Newton. Right? And so, for example, if I push with 100 newtons on the wall is going to push back on me with a force of 100 newtons. Okay, so actually this one's tough enough that I think I want to try to show you guys an example. I'm going to go to a PHET website. Just one second here. I'm going to go to a little website for you and show you something kind of neat. I think you'll like it. Actually, if you follow along, you will really understand something important. This is the PHET website. Okay. PHET, I'm looking at forces and motion, and I put that link for you. So we're going to start off with forces. And what happens when you put some people here. This is like a tug of war, right? If I click go and they're the same force, so we can actually show the sum of the forces is 0. This is called the net force. So when there's more than one force and they are acting on this object, see here's 50 newtons and 50 newtons, but one is this way and one is this way, they cancel each other out. Okay, so you actually don't see anything happen, right? So pause. Okay, let's see. Let's put a second person here. Well, now one side is bigger than the other. And so when I click go, what's going to happen? They start moving. Okay, now pause for a second. So what happens is it is now moving. Okay, so now because one force on one side was bigger than the other, there was a net force of 50 newtons, right? You don't have to know the numbers or anything like that, just the concept. Now, what if, now that it is moving, what if I take away this player? So now there's a sum of the forces is 0, right? They're still pulling the same strength, but it's already moving. What will it do? It'll keep moving the way that it's already moving, right? In order to change it, you need to introduce a difference in the force. So if you watch what's going to happen, because now I have a net force which is the opposite to the direction that I'm moving, it should slow me down, stop me, and actually start moving me the other direction, right? So this is actually the way forces go. So actually, I'm going to remove this, right? And it'll keep moving already the way that it's moving until I pull in some more force. And so then it slows me down, stops me, starts pulling me the other direction. Okay, but if I match the forces, then it will move at a constant velocity. I need a net force to slow it down and stop it. Okay, so that's the concept of force. So when you push on something, right, you cause it to speed up, right? You accelerate it. And that's what's going on. So this thing actually would show me, if I reset, let me try it again. If I press, I'm gonna put the speed here. If I press on it, it speeds up, okay? If I pull on it or push the other direction, it slows down, right? Okay, now in the real world, we have friction. So in the real world, when you push, right, there's always some friction pushing back on you to try to slow down. And eventually it slows down and stops. Now, it's not stopping because it wanted to stop. It's stopping because there was a force of friction acting on it. Now, if you take away the friction, what's kind of cool is if I start moving it and then I let go, it keeps moving because there's nothing to slow it down and stop it without friction. Turn the friction on. Let's put lots of friction now, actually, right? Slows down faster. Okay, now, so this makes it harder to move. But anyways, that's the idea. Okay, the last one. This is kind of cool. If you put this cup of water here, this is kind of a crazy thing. If I accelerate it, look what happens to the level of the water. Actually, I'll just turn off. It doesn't matter if there's friction or not, right? You can see the water tilts as long as I'm pushing and then goes back to. So the demo that I did with the cup of water on the tray is actually an example of this. Okay. All right, so back to our story. Okay, so sorry, just realized I want to tell you a little bit more. Okay, so one of the things that's kind of important to understand, and I wish you were in the classroom with me because that it would be more effective, but I would like you to know something important. That if you are a person, right? I mean, you are a person, obviously, and you have your arms and your legs. What's really kind of critical to understand is you cannot move yourself. And the reason is that any forces that you apply to yourself are called internal forces, right? Your arms are connected to you. So I pull on my arm, I pull on my arm. I can't make myself go anywhere. Actually, it would be kind of amazing if I could just pull up on myself, right? I could lift myself into the air. I could start flying. That would be amazing. I really want that, but you can't do that. So that's a rule, right? It says that in order to make the motion change, you need an outside force. So I want to tell you an idea that you may not know already, but you cannot move yourself, and you have never been able to. It is not possible. And so what I'd like you to know from now on is that when you think you are moving yourself, there's actually somebody else or something else that's making you move. Okay? There must be an outside force that makes it happen, right? So every step that you take as you walk around, it's not you that's making you move, right? And you're like, wait, I'm making myself. No, you're not. And I'd like you to understand that. So every step you take, I'll be watching you. Just kidding. Okay, that's my joke. I love the police. Okay, never mind. So every step that you take, how does it work, right? If you analyze the motion very carefully, has anybody ever tried to walk on ice, by the way? Because that's actually helps you understand how this works. It's really difficult. It's so slippery, right? You need friction. So the way that you work, the way that you walk is you push back on the ground, and the ground pushes forward on you. So you are the action. Your force pushes back on the ground. My foot, listen to the words, my foot pushes back on the ground. The equal but opposite means that the ground pushes forward as strongly as I push back. The ground is what's pushing me forward and making me move, right? It's not me, it's the ground. And so it's a weird idea, but it's an important idea that you actually will never make yourself move. It's only a reaction. So when you go to space and there's no sense of gravity, and I'll talk about why in just a minute. In order to move around, actually what you do is you push off of the walls, right? And so again, try to understand what's going on. You push on the wall pushes back on you, and that's the way that you actually, you're gonna move. Same thing, right? Let's say you wanna jump off of the ground. How do you do that? You push on the ground, and the ground pushes, you push down on the ground pushes up on you. And if you watch the video when I'm driving the rocket car, isn't that awesome? The way it works is the rocket engine pushes the gases this way, and the gases push the rocket in the opposite direction. That's the way things work in space when there's no gravity to push off of. Okay, called the law of action, reaction. Okay, so we are up to a fourth law, which is the law of gravity. And you want to write this down. The law of gravity is this equation, right? The force of gravity between two objects that have mass. This was Newton's big idea. He said that all objects that have mass are attracted to each other. And the strength of the force of attraction is this formula right here. So in words, it says that the force of gravity is directly proportional to the product of the masses and inversely proportional to the distance between them squared. Okay, so this formula is a little bit complicated, but you don't have to do any real calculations, but you need to understand how it works. Okay, so please follow along with me. So every object that has mass, including you, right? In fact, one of the most important ones is you are attracted to the Earth. But anyways, two objects have mass, and the formula for the force of gravity is big G. This is called the universal gravitational constant. In our class, we don't even use it. It's just there for doing calculations. The mass number 1, the mass number 2 divided by the distance between them squared. Okay, and I'm going to describe how this works. So if you wanted to know, I'll tell you what it is. G is a number, 6.67 times 10 to the negative 11 power, very small number, right? Newtons times a meter squared divided by a kilogram squared. Now, if you wanted to do calculations, you would need to put in the numbers for mass. You would need to use kilograms, right? Which is kg. And if you want to put in the distance between them, r, you'd need to use meters. Okay, we don't do the calculations in this class, so you don't have to worry about it. okay? But you need to understand the concept, okay? So now we're going to start off and ask the question, all right, well, where is this mass located? And this was a big thing, right? Newton had to actually answer this question. You need to know the answer to this question. Where is this mass located? And it turns out mathematically, it's right here at the center of it. And it has a name that you need to know. It's called the center of mass, or the center of gravity, okay? Center of mass. And where's the center of this one, right? This is the center of mass. So where is an object located? And the answer is at the center of mass. So where is the distance between them? So the answer is you have to draw a line from the center to the center. That's how it works, right? So the distance between them is going to be from center to center. So the reason why this turns out to be pretty key is that you and I experience a force of gravity because we are attracted to the Earth, right? We feel weight, right? We feel weight as the force of gravity. The force of gravity is pulling down on us, right? Towards the center of the Earth, no matter where you stand. Did you ever wonder why in Australia they don't feel upside down? And the answer is because they are pulled towards the center of the Earth, just like we are, right? There's no, it just turns out that they're on different sides of this globe, okay? So you and I are standing on the surface of the Earth. The Earth has a big mass and we have little tiny masses, okay? So if gravity is, the force of gravity, our weight is the force of gravity, right? That means that the Earth is pulling on us. But according to Newton's third law, if the Earth is pulling on us, then we are pulling on the Earth. How hard? Just as hard, right? So in fact, this is called our weight, right? So I could tell you my weight, my force of gravity. My force of gravity is about, oh man, it's pretty big. What is it about? What is my, oh man, okay, let's say I'm about 800 newtons, okay? So if I feel a force of gravity of 800 newtons, then the Earth must feel a force from me of 800 newtons. But compared to the size of the Earth, that's nothing, okay? All human beings combined weigh nothing compared to the Earth, have a mass of nothing compared to the Earth. Okay, so I want to share with you something kind of important, right? That we are standing on the Earth. So if you were not in my class, you were not in this class, you might say, are we touching the Earth? And the answer is, yeah, I'm touching the Earth. So how far away are you from the Earth? Some people would say zero distance, right? But that's not right. How far away are we? And it turns out that we are the radius of the Earth away, right? And if you remember, that's 6,400 kilometers, which is 6,400,000 meters, right? Now, again, you don't need to know, you need to know this, you don't need to know this, right? You just need to know the idea, okay? So you need to know a couple of things about this formula. And I'm going to show you the most important thing right now. What happens to this formula if you make one of these numbers get bigger, right? If either M1 or M2 gets bigger, then the force gets bigger because these are on the top. But what happens if you put in a bigger number down here, right? And the answer is, well, the answer gets smaller as a result of that. So again, what happens if to a person, what happens if a person has more mass? They feel a greater weight, right? What if they're twice as much mass as me? Then the answer is they'll feel a weight, which is twice as big, right? It's directly proportional. But I want to ask you one other question. Imagine I were to climb an enormous ladder. Imagine this giant ladder, right? And this ladder is so big, it turns out it's the radius of the Earth. It's huge, right? And actually, we don't even have the technology to build such a ladder. But if I were to climb this ladder and get up here, what would happen to the force of gravity? Would it be bigger? Would it be smaller? Would it be the same? Okay. And so you will have to answer this question on your next test. And the answer is the force of gravity is going to be smaller because I am further away. In fact, how far away am I from the Earth? Well, to get to the surface of the Earth is one radius of the Earth, but to get to the top of the ladder is another radius of the Earth. So what is the actual distance, it turns out? In this case, my radius, or my distance from the Earth, is 2 times the radius of the Earth. So if I go back to the formula, right, and I put in this thing right here, I want to show you what happens, right? The force of gravity, this didn't change. The mass of the Earth didn't change. My mass didn't change. The only thing that changes is, instead of putting in the radius of the Earth, right? I should have done it the first time like this, right? When I'm at the surface of the Earth, this is my weight, right? And I know what that is. What is it? It's 800 newtons. 800 newtons. Okay. What happens when I put in 2 times the radius of the Earth and squared, right? So what you want to notice is that the 2 gets squared and the radius of the Earth gets squared. So I end up with a big G, big M, little m over a 4 times the radius of the Earth squared. So it's the exact same thing, except there's a 4 down here. So it turns out I weigh 1/4 as much. So my weight at the top of the ladders is 200 newtons, 1/4 of 800. I just lost weight. How about that? So here's a question for you. Are the astronauts in the orbiting International Space Station, do they have a force of gravity? And the answer is, well, they're not very far away. Turns out they're only 400 kilometers above the surface of the Earth, right? And so the answer is, they're actually not that far away from the Earth. Remember, even at the top of my ladder, 6,400 kilometers, I still have weight. So they have weight too. But the funny thing is, this is a cool idea, that if you are falling, you feel weightless, right? And so that's actually the truth, is that the astronauts are falling, and so they feel weightless. The way that we feel weight when something holds us up. So whether it's your chair or your bed, you feel it. And so I'll just use a quick example. It's not a person, but I want to use, I got this table and I put a book on it, right? The book has a little mass, okay? And the book is sitting there, and if I watch it, it's not going to do anything. Why not? Well, it turns out that there is a force of gravity. There's a force of gravity, right? There's a weight. I know that because if I hold it over here, it falls, right? But if you watch the book on the table, the reason it's not moving is the table is pushing up. And you want to understand that the force of the table has to be as big as the force of gravity. So this is a very special situation. The net force is 0. And I'd like you to know the word for that. The word is equilibrium. That's called the equilibrium. So when you have equilibrium, the force is 0. Nothing seems to be happening. But the force of gravity is still there, right? There's a force that's just as big holding it up. And this turns out to be a big idea. And the only way that things fall is when they're not in equilibrium, okay? Not in equilibrium. So this turns out to be a big deal. So what Newton figured out is that the moon is actually falling around the Earth, okay? So I actually, let me see if I could just, I'm gonna bring up one more thing for you. This is called Newton's canon, and I actually put a link for you in the resources. Okay, here's Newton's canon, and if you fire the cannon, you can see that when I shoot the cannon, it falls. Okay, the faster I go, the further it goes. Right now, you see Newton figured out that because the Earth is a sphere, that if you go fast enough, something interesting, right? If you go fast enough, you see you actually might reach a point where you fall, but you actually don't get closer to the Earth. And you're falling, but you're falling and moving forward, and boom, you made it all the way around. And so that is what we call an orbit. So the moon, he said, is being pulled by gravity, which makes it fall, but it's moving forward so fast that it doesn't hit the Earth. It falls around the Earth. That is an orbit, and that's what's happening to the International Space Station. So why do the astronauts float around? The answer is because they are falling, and so they don't feel any weight. All right, we've covered a lot of concepts there. But basically, the idea is the further away you get, the weaker the force of gravity, the closer together, the stronger the force of gravity, and the more mass you have, the stronger the force of gravity. Okay. This is the acceleration near the surface of the Earth, and it turns out it's the same. But on the moon, it's only 1/6. Yeah, not a big deal. Moving forward. And our final big idea. This is a big deal. It turns out that if you see an object moving in a circle, then we know mathematically that there must be a force making it turn. And you see this turning is actually going to be to the side. So what do you remember, right? If you're moving forward and the force is to the side, does it speed you up or slow you down? Trick question. All it does is make you turn. So uniform circular motion, which means moving at a constant speed, you hear the word speed? Constant speed causes you to turn, which means you're changing your velocity, but it doesn't speed you up or slow you down. And it turns out that you need a force pointed towards the middle of the circle, and it has to be just the right amount. So the planets that orbit the sun travel with different speeds. Take a look right here. Mercury has the fastest speed. And why do you think that would be? Well, think about that for a moment. Mercury is the closest planet, right? Since gravity is so strong, it has to move really fast to avoid being captured and pulled into the sun. Venus, further away, doesn't move quite as fast. Earth, a little bit slower. Mars, a little bit slower. And you can see the further away you go, the slower the planets are traveling, okay? So this gives us a very important concept, right? And this is Newton's canon again, right? So that if you go faster and faster, you eventually fall around the Earth. But what happens if you go even faster? And the answer is if you go fast enough, then you can leave the Earth behind. You get on a rocket and you go fast enough, then you will actually be able to escape. So if you write down a definition, the escape velocity is the speed you need to be able to get away from a gravitational body. Okay, and so we won't do any calculations, but it's a little bit faster than you have to go just to orbit, right? So, but if you go fast enough, you will escape from the Earth, and later on we'll learn how to escape from a black hole. Okay, so that is chapter 3. Thank you for your attention, and good luck on your quiz and the exam that follows. Please ask any questions if you have them, and I will do